like to introduce Dr. Jessica Liu. She is currently an associate professor of astronomy at UC Berkeley. And before she was at Berkeley, she had received her undergraduate degree in physics from MIT in 2000, and then worked for a few years in Silicon Valley as a software engineer. She then went to UCLA for her PhD and earned her degree in 2008. And then she proceeded on to be a postdoctoral fellow at Caltech and also a postdoc at University of Hawaii Manoa, where eventually she joined the faculty of the Institute for Astronomy at University of Hawaii Manoa in 2013, and then came to the University of California system to be at UC Berkeley. This evening, she will tell us about black holes in the Milky Way galaxy. So thank you, Dr. Liu.
Thank you so much. Thanks. Thanks for sticking around. So small audiences are the best. That means you can ask any question at any time. Just stick your hand up or shout out the question. That's the best way for this lecture to go. Okay, so I'm going to tell you about our search for black holes in the Milky Way galaxy tonight. We have to start with, what is a black hole? Anyone know or have an idea of what they think a black hole is? No? What? Imploded star? Great, yeah, maybe. Some types of black holes are definitely imploded stars. Other guesses? What makes a black hole black? Something that sucks in the light, yeah, or prevents it from escaping. It's mass. It has to be pretty massive. Yeah, these are all correct. These are all good descriptions of a black hole. There's one that physicists especially like to call a black hole, and that's the term singularity. So a black hole fundamentally is some amount of mass over an infinitely tiny volume, almost zero volume. So the density goes to infinity, right? And when this happens, physicists scratch their heads and are puzzled and don't have equations to explain it, and so they call it a singularity, which just means, I don't know. So that's fundamentally what a black hole is. So a black hole has an interesting property. It has no surface that we know of. It only has what's called an event horizon. And that's just an imaginary line in space, whereas if you cross over that line, you'll never be able to escape the black hole. And that holds for both mass and light. So even if there's a ball of hot, gooey stuff at the center of a black hole and it's emitting lots of light, that light will never be able to escape. It'll just swirl around on the inside of the black hole. Okay, so black holes come in a couple of different varieties. First, there's what we call the ordinary black holes, if any of them can be ordinary. This is what happens when a very massive star dies. You take a star that's about 20 or 30 times as massive as our own sun. It lives its whole life, it exhausts all its fuel at the end, and it dies. When this occurs, it collapses. And it may cause a supernova explosion, but some part of it may be left over to implode in collapse into a black hole. Now, the black hole isn't as big. It only has sort of like a third or maybe a tenth of the mass of the original star. So we think black holes are massive. Their masses may be as high as starting at 3 solar masses, 3 times the mass of the sun, and may go all the way up to maybe 100 times as massive as the sun. These ordinary black holes were first predicted by theory. Theorists sat down, they grunched through some equations for gravity and general relativity, and they predicted this singularity, this existence of black holes that at the end of the life of a star. And in our own Milky Way galaxy, we speculate that there could be as many as 100 million, possibly up to 1 billion black holes just floating around in the Milky Way galaxy. The second type of black hole is a supermassive black hole. These things are behemoths. They're maybe 1 million to 1 billion times as massive as our sun, and they sit at the center of a whole galaxy. So anyone know what galaxy we live in? The Milky Way. Did anybody get to see it tonight? Is it up yet? Yeah, right. So you're looking at our home galaxy, the Milky Way. So our Milky Way has hundreds of billions of stars, maybe 100 million to 1 billion black holes, but only one supermassive black hole right at its center. And now when you go see those wonderful new JWST images of all these galaxies in the distant universe, we do think that each one of those has its own one supermassive black hole at the center and swarm of stellar mass black holes. So this supermassive variety was actually not predicted by theory, but was instead first suggested by observations instead. And as I said, almost one in every galaxy. Yep, go ahead.
Where is the
Yeah, so where do those big behemoths come from? That's an excellent question. We don't honestly know. We have some speculations. Is it the merger of lots of small black holes? Does it start with a seed, ordinary black hole, and then accrete a lot of mass and gas and other stars? Or does it need a bigger seed from something more exotic, maybe what we call a primordial black hole born right after the Big Bang? All of those are plausible hypotheses, and we need the next generation of telescopes to answer that question.
Along with that, there's a big gap between two sets of numbers.
Is there anything in between?
Between those, but nothing stays between that.
Yeah. Why are the ordinary ones small and the supermassive ones so big? Is there anything in between? Astronomers with our lovely naming schemes, we call those intermediate mass black holes. Very exciting, right? And that's an active area we're looking today to try and find intermediate mass black holes in that in-between range. And a lot of people have claimed that they've discovered one, but the claims have come and gone with new data. So we're really still looking for that definitive case of an intermediate mass black hole to help us tell how we get from one to the other. Yeah?
Is there any difference, this is kind of a dumb question, but like, the singularity of an ordinary black hole compared to the singularity of a supermassive black hole, do they have any different properties besides having a bigger event horizon?
That's an excellent question. Honestly, one of the coolest things about black holes is we think they're the same regardless of their size. If we could make a black hole on Earth, a tiny black hole, it would have the same properties, infinite density and that event horizon, as a supermassive black hole. You just scale the whole system up. So we don't think today, although singularity means we don't really know, we don't think there's any difference between the types of black holes. There may be some little things like the spins of the black holes. Do some spin faster? Do big ones spin slower? Those are things we're still going to discover in the next coming decades or centuries. Okay, so we know a lot in theory about black holes, a little bit in observations. Where do we go to find them? Where do we make these observations, particularly of the ordinary black holes, which is what I'm going to focus on for the rest of the talk today. So black holes really are stellar ghosts. They don't emit light themselves. They're dark, very dark, infinitely dark. So how do we find them? There's two ways historically that we found black holes. First, we can see them indirectly. We see them when they have a companion that's close by, a very close star. That star, the black hole tugs off a little bit of mass, a little bit of gas, makes an accretion disk. That's this orange round thing that you're looking. The gas flows into the black hole, and just before it passes through the event horizon, it gets extremely hot and it glows in X-rays. So those X-rays and that sort of variable brightening and dimming of X-rays is a sign that you may have a black hole. So many of the black holes that we found in our Milky Way are these X-ray binary systems. Today, we can also now hear, in quotes, black holes. We can see them or discover them not just from electromagnetic rays, X-rays coming towards us or any optical light. Now we can actually see ripples in space-time that come from the merging of two black holes. This is brand new. We've only built these gravitational wave detectors for the first time in the last 5 or so years. But now that we have this unknown portion of the universe that we never could detect before, but now is open to us, we're seeing these merging black holes throughout the universe. Now we're up to 100, at least more than 100 merged black holes. Okay, so we are now for the first time being able to see and hear black holes in binary systems. Mm-hmm.
A question about the previous one in the visual, which showed the ripples like pretty linear. Is it actually physically linear, or is it kind of like an arc?
So you're talking about these orange rings here? Yeah, so actually most of these disks will be a little bit flared, we think. But this is pretty close. The ripples or gappy things, we don't know if those exist or not. This is an artist's rendition. To imagine taking this and putting it, a million times further away. There's not much detail we can see, but we can see the X-rays that come from it, just not the detail here. Okay, so unfortunately, all of these ways of finding black holes relies on them being in binaries, having a companion. So this is a beautiful plot that shows the complete demographic census of black holes today. All these black holes that you see in blue are black holes that were found with gravitational waves, those ripples in space-time, as black holes merge. All the ones shown in pink are those found as X-ray binaries that had a star companion that was dumping some gas on it. And everything that's shown in yellow is actually a neutron star, not a black hole, which is still a stellar ghost, but it's still a star that's holding itself up from neutron pressure and has a surface to it. So it doesn't have an event horizon, not a true black hole. So these are the stellar ghosts we know about. They're all in binary systems. The horizontal axis doesn't mean anything. It just makes this pretty butterfly pattern. So, okay. So if we want to find the black holes that aren't in binaries, which we think are most black holes, what are we going to do? We have all these population already. What good is it? Why bother looking for the free-floating single black holes anyways? Well, with only the binary population, there's a lot that we don't know. Really simple things like what's the total number of black holes in the Milky Way? We don't know the answer to that. Which stars turn into black holes? I said it was 30 times as massive as our sun. Those stars die and turn into black holes. Some of that is just pencil and paper calculation. We don't actually have proof that that is the case. What is the black hole mass distribution? How big do they get? Are they all 5 solar masses, 10 solar masses? Do they get up to 100 solar masses or even bigger? How many are in binaries, and how often do they merge? It's hard to interpret those gravitational wave measurements without answering that question, which means we need those free-floating measurements. And do black holes, when they're born, if they are born with a supernova explosion, do they get kicks? Are they ejected from their companions? And do primordial black holes exist? These would be black holes born during or right after the Big Bang. So a lot of really basic questions about black holes that still remain unanswered. No, go for it.
Is there any way to tell the age of a black hole?
No, not that we know of today. Black holes don't emit light, so we have no ability to know the age of a black hole.
So do you tell the age of stuff by the light?
For stars, we can start to tell some age by not just the light, but what's called the spectrum. And looking at the chemical fingerprint in the star, we can tell a little bit about how old it might be. But we don't have any such fingerprint for a black hole. All right, so we want to find free-floating black holes to answer these questions. These are single black holes, just floating around in the Milky Way without a companion, not accreting any gas, not going to merge anytime soon. So what do we do? How might we find them? Well, turns out they're plentiful. You can imagine with a few 100 million black holes in the Milky Way, they should be all over the place. This is just showing a simulation of how many we think there are. Rather than go through this, actually the best thing to do is just hold your thumb up. If you put your thumb up towards the center of the Milky Way, that's about the size of a full moon or half a degree. There should be at least 1,000, if not 10,000 black holes in just that little patch of your thumb, right? So there's a lot of black holes to be found if we could just find them somehow. Well, what are we going to do? We can wait and use the black hole's gravity against it and wait for a star to pass behind it. And when that happens, we get a magic effect that looks like this. It's called gravitational lensing. Obviously, this is not a black hole. This is a wine glass. But the principle is actually exactly the same. So you can go practice at home, pick up a wine glass and look at the bottom and hold it up to a light source, and like a candle up in the left corner there. And then what happens when you put it past the wine glass in front of it, you'll see the single point-like light source turn into all kinds of crazy things, like a ring, or this multiple images. Suddenly the candle becomes 2, and they're warped, right? So even more, multiple images up there. So this is just the property of lensing. This is glass acting as a lens. The gravity of a black hole can do the exact same thing. It warps the space-time around it, and it bends light in ways that aren't straight paths anymore. That's called gravitational lensing, and that's exactly what we're going to use to try to find free-floating black holes. Gravitational lensing has been observed in astronomy for a long time, but not from black holes, but instead from whole galaxies. If we look towards the deep universe, sometimes we see 2 galaxies that happen to be one in front of the other. And they act as, the foreground one acts as a gravitational lens and can make multiple images, just like you see up there. That's a big galaxy in red, lensing a far distant background galaxy in blue, but it makes 4 images of it. Right? That's pretty incredible. Now, these galaxy images are spectacular. This is real astronomy pictures. We can see all those multiple images. Unfortunately, if you take a much closer black hole in our Milky Way, you can't resolve all these images. It just looks like a single point of light. So here's the geometry, or here's the artist's rendition of what we think this might look like if we found a black hole very close to us. And I mean within our solar system, which is not going to happen. So you have to be really close, but you can see this is a true rendering of how a black hole would change the background light that's coming from the galaxy, right? It really does warp everything, and you see these lovely rings of all the images from behind it. Okay, here's the geometry of the system that we're talking about. Sorry for the white background, it'll definitely wake you up. So take a background star on the left. The light coming from that star would normally, some of it would go away from us. Only one light beam would come towards us. As those light rays pass close to a black hole or a neutron star or other stars, anything with mass, it encounters this warped space-time, and the light rays get bent back towards us. And then eventually that makes those multiple images, and the light from those multiple images is what comes to our telescopes. So this is gravitational lensing, and we call it, in the Milky Way, we call it microlensing because unfortunately we can't see the multiple images. We just still see a single star. Okay, so how can we see it? What happens? Well, let's look at it face on instead. So here's a black hole, and you're going to see that background star is going to pass behind it. As it does, you see the multiple images that form temporarily. It warps, arcs, and then moves along on its way. Now, if I play this again, oops, sorry. If I play it again, now look at the lower plots. Here you see the brightness of that star. It gets brighter for a time and fades away. And the same thing is true for the path of the star on the sky. It no longer moves in a straight line. It has these little excursions in its position over time. So that's the signal that we're looking for. Even though we can't see the multiple images, we can see this brightening effect, which we say photometry or brightness, and we can see this position effect, which we call astrometry or position. So that's the sign of gravitational lensing for a black hole in the Milky Way. Okay, here it is in more detail. Just showing you again, over time, this is the signal we're looking for on the bottom, the brightening over time and fading away. If you have just the brightening, unfortunately, you can't get any information about the lens mass. That thing that's moving in front of it, we don't know if it's 10 times as massive as our sun, 1 times the mass of our sun, or 1 Jupiter mass. It could be a planet all the way to a star to a black hole. We just don't know. We have to have that position measurement. So now I'm going to play the same movie for the position measurement, focus in on the red and the green line. The green line is what the star would look like if there wasn't a black hole in front of it. The red line is what it would look like if a black hole was in front of it. So again, you get this little excursion in the position. Once you have that, you can make a measurement of how big the difference is, and that gives you information about the mass of the lens. So it's only with the combination of the brightening, the photometry, and the position, the astrometry, that we can tell if we have a black hole. So now this is still simulation, but back when we started this program in 2009, well, many years ago now, we had to prove that it would work. So we did a lot of simulation work, even showed mock observations of what we thought the signal might look like if we were able to find it. And I just showed this because you can see how small the effect is. So again, straight line is what you would expect with no lens or no black hole, and the solid green line is what you would expect if there was a black hole, and you can see some mock observations. It's a pretty small difference that we're looking for, right? Okay, so we also showed that it did matter if you change it from a black hole to a star. The black hole is in black, the star is in red. The size of that position signal gets bigger or smaller. So the black holes should have the biggest position signal difference. All right, now, microlensing is pretty rare. Remember, we have to have a star and black hole become aligned. So in fact, only 1 in a million stars produce gravitational lenses, and only 1% of those would be black holes. So we have to basically look at 100 million stars a year if we want to find one black hole, right? So where can we do that? Where can we find 100 million stars to look at? Well, we can towards the center of our galaxy. So here's a picture from the top down of our galaxy, which we could never make in reality. There we are on Earth or around our sun in blue. And if we look towards the center of the galaxy, we see millions and millions, hundreds of millions of stars. And so that's a great place to look to find that chance alignment between a black hole and a star, which is exactly what we're hunting for. So we go out, hopefully you just saw a picture almost like this, of the Milky Way. You go out there, you find the brightest part of the Milky Way, that part up there where you see all those white stars. That's the most dense portion that we can see by optical light, at least. And we go out there and we watch that patch of the sky. We watch it every day, again and again and again, for years. We do this for microlensing, dedicated surveys to look for this gravitational lensing signal, but only the brightening side of it. So there are whole telescopes dedicated to finding microlensing events, and today they're finding almost 1,000 microlensing events per year with this photometry brightening and fading away, right? And they're surveying that patch of the sky. Unfortunately, those same telescopes can't give us the position measurement. They're small, they're fairly small telescopes. We need a much bigger or better telescope to measure the positional offsets. So we take the candidates that we identify, those 1,000 microlensing events per year. We'd love to observe all of them with the Keck telescope, which is 10 meters across, or the Hubble Space Telescope, which provides very sharp images from above the atmosphere. But they won't let me use all the telescope time. So unfortunately, we can only look at a few such events. We have to pick out which of those 1,000 might be the best black hole candidates. That means we have to go back to simulations, because from the data, it's almost impossible to tell which of these might be a black hole or not. So we mock up a Milky Way in our computer. These are simulations showing a bunch of mock microlensing events, not real ones. But now I can, since I made it at the computer, I can tell you which ones are stars and which ones are black holes. So we can look at their properties, we can look at how long the microlensing events are, and we can look at that positional offset, which are the two things we'd like to measure. So you can see it's pretty clear from this plot, the stars are in green, but the black holes all like to cluster to the right side of the figure. They all like to have long durations. So our best bet is to take all those 1,000 microlensing events and pick out the few that have very long durations, maybe a year-long microlensing event. So there's about 10 of those candidates a year, so that really shrinks down the sample size quite a bit. And so we take 10 of those, pick out the best 2 or 3, and try to start observing them with the position measurement machines. So what are those machines? There's only 2 that really exist. There's the Keck Observatory and the Hubble Space Telescope. So these are the 2 facilities that we've been using to try to make those positional measurements that I showed you. Now, why those 2? So Hubble Space Telescope is in space. It's a 2.4 meter telescope, close to the same size as the telescopes you were looking through tonight, right? So it's not a huge telescope, but it's in space, which means it gets exquisitely sharp views. None of that blurring from Earth's atmosphere that makes the stars twinkle, right? So that gives us a really, really good way to measure the positions of these microlensing events. What about the Keck telescopes? They are 10 meters across. If you're a telescope fan, you must get to Mauna Kea and see one of these big 8 or 10 meter telescopes. They're gigantic. However, they all suffer from the Earth's atmosphere blurring. So they don't provide such sharp images on their own until you equip them with a special technology called adaptive optics. And adaptive optics attempts to correct the blurring of the Earth's atmosphere. Right? It's a very amazing technology. However, it requires a bright star to measure the turbulence and then correct it. And we don't have a bright star everywhere we look. There are lots of stars towards the center of the galaxy, but they're not often bright enough to make this measurement. That's what the lasers are for. We use a laser to shine up and illuminate a thin layer of neutral sodium at 90 kilometers above us, above our heads, all deposited there from micrometeorites. So it rains down sodium through the atmosphere, and at 90 kilometers, the sodium's neutral. We shine our lasers up, it fluoresces and makes the sodium atoms glow, and to us, that looks like a star. And we can do this and make an incredibly bright star. And in fact, we use that star to measure the turbulence and correct it with our adaptive optic systems. So that's what this picture is showing here. These are the 2 Keck telescopes plus Gemini and Subaru. So 4 laser-equipped telescopes all shining their lasers and studying the center of the galaxy all at the same time. We use this technology to search for black holes in the exact same way. The very first time we started this project, I wasn't a professor yet at all. I was a postdoc. We were trying, this was very experimental. We had to prove to people that it would work, so we tried it for the first time. We looked at a crowded star field towards the center. We knew we had a gravitational lensing candidate in the green circle. We had this lovely long duration light curve, so we thought it was a good candidate for a black hole. And at about here, at the peak of the event, we pointed Keck towards the event and we started making measurements. measurements. And we just kept making measurements for several years in a row. And this is what we saw in the position measurements. This is the trajectory on the sky. Remember, we're looking for something that's not a straight line. What do you think? Does it look straight to you? Looks pretty straight. As you can imagine, I was pretty disappointed. I was out job hunting, trying to get a job, and boy, would it have been nice to have discovered a black hole then, but sorry, out of luck. But despite that, we could prove that the technique worked. We didn't see a signal, but that proved to everyone that this thing was small. It had low mass. It was 1 solar mass or so, about the same size as our sun. It was definitely not a black hole. So that was good enough to get us to start the second batch, which I'll get to here. Which we started 2 batches from 2 competing teams, one with Keck telescope and one with Hubble Space Telescope. And we've been studying that second batch for the last 5 or 6 or 7 years or so. And here's one of the candidates. This is the candidate we think is the best one that may harbor a black hole. So here's first the images that we took from the ground with the Ogle Observatory. And you can see if I play that again, you can watch the star in the middle. You can see it gets bright, really bright for a time and then fades away. A sure sign of gravitational lensing. So again, at around the peak, Hubble started observing the event. And this is what we saw on the sky. So you see each of those measurements as they pop up. Those were taken over many years. You see the time running there. And what we were looking for is a small deviation from the dashed gray line. Can you see, does it look straight to you or not? The orange line goes through it better than the gray line, right? Yeah, so maybe I'll show you a better view. Let's subtract off the bulk motion first, and then we can see if it truly is moving in a straight line. So here on the bottom, we're showing the the east-west motion, and on this panel, the north-south motion over time. If this thing was moving straight, all its measurements should line up with that dashed black line. And so you can see right away that not all of them fall on the dashed black line. It shows this weird curvature, this weird deviation from the straight line. In the early years, it's on the straight line, then it moves away from it, and then goes back to it. That's exactly the signal we were looking for. So we think this candidate is the best candidate for a black hole, or, strangely, possibly a neutron star. So unfortunately, with this target, it's so low mass that it had 2 possible solutions. Either a black hole of 3.7 times as massive as our sun, or a neutron star with a slightly less mass. We know this thing is dark, so it is definitely a stellar ghost. But at this mass range, we're not sure yet if it's a neutron star or a black hole. Fortunately for us, we have 1 more measurement coming from the Hubble Space Telescope later this year, and we hope that will help us distinguish between these 2. All right, so now just as exciting as finding the first black hole with gravitational lensing is looking at all of the ones that didn't contain black holes too, because the number of events that we looked at was starting to be an interesting sample. We could say, yeah, we expected to find 3 black holes, but we only found 1. What does that tell us about the population in the Milky Way? Again, we go back to simulations. So again, these are just a couple of plots of different simulations, and you can see the black holes in black and all the stars and white dwarfs and neutron stars in blue. And then all the colorful contours are all the candidates we looked at, not just the black holes. So we use all of them together to ask the question, how many black holes do we think are in the Milky Way, given that we only found 1 when we looked at 5 events? It's a small sample so far, but so far everything points to, yes, indeed, there are about 200 million black holes in the Milky Way. So if you extrapolate that, that means there's a black hole within about 80 light years of the solar system, not too terribly far away. We expected to find about this many, about 20% to be black holes in our sample of 5. We're getting a bigger and bigger sample all the time. So over time, that error bar will shrink, and then we'll really start to be able to say, yeah, this is what we predicted, or no, there's some difference in the black hole population. But this is still early days. Okay, so it's exciting that we have our first black hole, but we're really, really at the bleeding edge of technology when we're trying to make this measurement. So how can we do better? What's next in our search for black holes? Well, we've been looking mostly towards the center of the Milky Way, but there's a lot more stars out there, and presumably a lot more black holes too. So we'd really like to expand where we search for these gravitational lensing events. And we're working on that. We're working on expanding not just from the blue colored patches, but all across the Milky Way with bigger surveys that look at all the sky all the time. We're also trying to get better position measurements. Turns out we're limited there by our instrumentation. The optics that we build, the instruments that we build, have their own distortions that can look like position offsets sometimes. So we're building some extra hardware in to be able to measure those and get rid of them so that our position measurements are more precise than we've ever made before. We can build new telescopes. There's a telescope we're building right now called the Nancy Grace Roman Space Telescope. And this telescope has a dedicated microlensing mission in it. And we can use that microlensing mission to find black holes, much more faint than what we've done today, many more stars that it's observing. Now, unfortunately, their microlensing mission is set out to find planets, but we're going to hijack the mission and turn it into black hole searching instead. But don't tell them. Or we can build a much bigger telescope, not for space, but for the ground, and equip it with our best adaptive optics systems. So this is showing the Keck 10-meter telescope, which exists today, 2 of them, in fact. But the next generation is 20, 30, 40 meters or larger. So this will give us much more precise positions, much higher resolution images. Just to give you a flavor for what this is going to look like, this panel shows you current Keck on the far left. The middle is the best that we could possibly upgrade the Keck telescopes. And then the right is this 30-meter telescope that we hope someday to build. And I'll show you just this animation that we put together to show you how much more detail you can see, how many more stars you can see, and how well you can measure their positions on the sky as they're moving around. So we're really looking forward to the era of these next generation of large telescopes. Yeah? So there are 3 next-generation large ground telescopes, all with very, very mature plans. And actually, the mirrors are being built as we speak. There are pieces of the mirror that have been manufactured, and they're being polished, and structures are being built. There's 2 in Chile and 1 that supposed to be in Hawaii. The 2 in Chile are actively being constructed. The earth is being dug. The one in Hawaii hasn't started construction on the mountaintop yet, but does have hardware that's being made. Okay, and then last but not least, I'd be remiss if I don't mention the James Webb Space Telescope. So we are looking for black holes, not just free-floating, but also in binaries too. This is an example of a candidate black hole that we've potentially discovered towards the very center of the galaxy that's around the supermassive black hole there. We've been staring at that patch of the sky for the last 25 years, making very good position measurements. And we see some pretty peculiar stars that are wobbling on the sky. And that wobble, we think, is big enough to say that it's wobbling around a stellar mass black hole, an ordinary black hole. Now, we don't know for sure. We have to prove this. And we're hoping to starting to use, in this August actually, James Webb Space Telescope observations to prove whether this is actually a black hole with a star orbiting around it, all orbiting the supermassive black hole. So that's pretty exciting. And that'll take some time to verify, but that should come in the next couple of years. Mm-hmm. When black holes merge, they usually, if it's just 2 isolated black holes, when they merge, they produce ripples in space-time called gravitational waves. And those gravitational waves propagate all the way out from all the way through the universe, and we can now detect those. So those LIGO, or gravitational wave black holes I mentioned earlier, those are all merging black holes.
Does that change anything about the size?
It changes their mass, so the mass goes up, and the event horizon moves out correspondingly. Sometimes when they merge, a little bit of mass we think is lost in energy in those gravitational waves. The mosquitoes and flies are dropping. Sorry about that. Yeah, so they do grow in size through mergers. All right, so I'd just like to close and say that the hunt for black holes of all kinds, both in binaries and free-floating, is really just beginning. A decade ago, people were finding the first exoplanets, and now there's thousands known. I really think black holes is in the same territory. The early days, we're finding a few, the first of every kind in different windows. electromagnetic or gravitational waves. But I think a decade from now, we'll be in the ballpark of having thousands of black holes known of all these different varieties, and hopefully answering those questions that I posed at the beginning. And I'm not alone in this endeavor. You get lectures from lone astronomers, but really there's a huge team behind us. In particular, I'd like to thank the incredible undergraduate and graduate students that I work with in my group and beyond. And there's a huge team of people working on multiple telescopes and making all of them possible. You heard Lick employs something like 30 or 40 people just to get Lick Observatory to run. Keck has the same, Hubble has thousands of people. So all of them, we need every single one of them to make these measurements possible and really tell us a lot more about the black hole population in the universe. Thanks.